Covered everything in the lab classes, so I will not repeat. The only thing I did not cover, I will do it here. That is the principle of pattern multiplication. Second thing we do, at least we'll start today at the helical antennas. Okay, so we can start. This is my z axis, this is my y axis. Okay, and then here we have two antennas, two dipole antennas, but any antennas for the say for our discussion, we assume that they are dipole antennas. This is my antenna 0. This is excited at I0. The phase is 0 degree or 0 radians. When I'm not making 0 degrees, let us make it 0 radians. Second antenna. This is antenna 1. This is I0 minus alpha radians. Okay. This is the P is the point of observation. Okay. This distance is R0. This distance is R1. The mutual separation between the antennas are D. Okay. This angle we have defined to be phi. Right? So obviously, as we had seen many times, this distance is D cos phi. This we had seen. Okay. This is basically a repetition of what we had done already. Nothing new. But this topic I didn't cover, so in the lab, so I will do it. Right. Now, what is the? We assume that both the antennas, they are Hertzian dipole antennas. Okay. So what is the electric field, and we assume far field? Two things. We assume number one, both antennas are Hertzian dipole antennas, and number two, we assume far fields. Okay. Now, what is the far field expression of a Hertzian dipole antenna? We had discussed this in the classes before. What is the far field expression for a Hertzian dipole? E theta, this was j eta naught, eta is 125, okay, k I0 L sin theta by 4 pi r. This we had seen in the Hertzian-Dipole class, okay. So the question we are asking is, what is the electric field at point P? What is E at point P? Or rather E theta, okay. Obviously, because the Hertzian dipole at the far field only E theta exists. E phi doesn't exist anywhere, and ER it dies down for the large distances from the antenna, okay. This we had already seen. So clearly E equal to a theta j eta k I0 L sin theta by 4 pi times e to the power of jk r0 by r0 plus e to the power of jk r1 e to the power of minus j alpha by r1. Can we write this? Can we write this? This is due to antenna 0. This is due to antenna 1. Left part, yes. Is it okay to write this? Downwards. Oh, there will be a e to the power minus j here. This is what I have missed. This will be there. Is it okay? We have simply the total field, of course, will be the sum of the electric fields due to antenna 0 and antenna 1, right? That's what we have done. Now we will use for far fields 1 by r0 is almost same as 1 by r1, and e to the power of minus jk r1, that is very similar to e to the power of minus jk r0 plus d of cos phi. Is it okay? We have discussed this also. Why? This is point number 1 and point number 2. Agreed? All of you? Okay, anybody else? Anybody else having doubts here? Why this is, why we can write this? Anybody else? Anything? Anybody else? Have any questions? Okay, so we move on. So we replace this, R1 and this e to the power of jk r1 by these two expressions. So what do we get? E equal to a theta j eta I0 k L sin theta by 4 pi r0 e to the power of gk r0 1 plus e to the power of j k d cos phi plus alpha. Is it okay to write this? Okay, Arpit, this is pattern multiplication, basically on antenna arrays. Okay, this is basically what we have done. What we have done here is we have simply repeating what we had done in the lab classes. I specifically did not touch this topic, but this topic is very important for antenna arrays. Okay, so that's why I'm going to teach you. Don't worry, I will give the recording so you can see the later the parts we have missed. Okay, so can we write this? Right? Okay. Now what did we do? We take this equal to psi kd cos phi plus alpha equal to psi. So we had E equal to a theta j eta I0 k L sin theta one into the power of psi. Okay. So see here what the point I want to make. This thing we have already done for in the lab classes, right? But the point I want to specifically make here is this. What is this red circle path? What is this which is coming in the red circle? What is that? E theta, yes. E theta what? E theta is correct, but E theta what? R0 means, if you see here, wow, it's very good, happy coincidence. Can I just, yeah, very good. Just compare these two things. What do you see? If you compare these two things, what do you see? The two red marked things side by side. What do you think? What is your conclusion? Okay, R is replaced by R0, okay, and has a theta. Okay, there is a, because this is a E theta part, right? So these two, can we say that these two red circle things are the same? R may be replaced by R0, fine. Can we say that these two red circle things are the same? Yes. And now tell me, what is this? What is this? This is the electric field, the E theta component of the electric far field by a single Hertzian dipole, right? The quantity at the left is the far field E theta by a single Hertzian dipole, right? Exactly. Now, what is the green thing? Just one second. What is the green circle thing? What is the green circle thing? Why is the green circle thing coming? So this red circle thing, we have concluded that this is the this is the electric field, actually far field E theta by a single antenna. So what is the green thing? What is the green thing? How and why is the green thing coming? The red thing, we saw that is due to one single antenna. How and why is the green thing coming? Anybody? Okay, fine, no problem, no problem. If you are not able to right now, let us go a little bit further, then maybe we can understand. This thing, I am writing this to be as a E theta, okay? This entire red thing, I am for my convenience, I am I am writing to be E theta. So E equal to E theta 1 e to the power of j psi, where E theta is this thing. Okay? Let us move on. Let us see. You can get something or not. We can write this. We can write this. No problem. What is the magnitude of this quantity? This will be magnitude of 2 is 2. Magnitude of E theta and magnitude of this quantity. Clearly, the magnitude of this quantity, this part, this is equal to 1. Okay? The magnitude of this e to the power of j psi by 2 is 1. So we can ignore it. What is this? This is equal to cos psi by 2. So, right? Now tell me, can you tell me why this cos term is coming? Can you tell me why this cos term is coming? Can you tell me why this cost term is coming? We have discussed this, I think, many times when we discussed the antenna arrays in the labs. I think I've done for both groups. Why this cost term is coming? What does this cost term signify? And we have once we have also have modified formula. Yes, we have also modified this phi to our choice so that we can have a the phase difference. Yes, phase difference between what? You still have, by the way, you still have the phi if the alpha is 0. For your help, I am writing what is phi. Phi is this. From where this cos phi by 2 is coming? This is coming because of the array, right? If we had only one antenna, this term would not have been there. Think that, assume that this antenna 2, this antenna was not there, then we will simply have this, the red part and not the green part. If we only had antenna 0, we would only had the red part and not the green part. Do you agree with this? If we only had antenna 0 and not antenna 1, we would have only had the red part in our equation and not the green part. Do you agree with this statement if I say that? Right? So the green part is coming because there are more than one antenna. Assuming that if there was an antenna 2 somewhere, think that if there was an antenna 2 somewhere, we could have had another term here. Agreed? If we had another antenna, if we assume that we had another antenna, we would have another term in the green bracket due to the third antenna, right? Do you agree? Correct. But okay, we don't have, so let us ignore that. What the I mean. Okay. So this red thing, it is coming, the red expression in the red, it is coming due to one single antenna, the pattern due to one single antenna, and the terms in green, they are the pattern due to the array. Right? The terms in the red, they are the terms due to one single antenna, and the term in the green, it is coming due to the array. Agreed? Okay? Can we say this? And what how to find the overall pattern? It is the product of the red term and the green term. The overall pattern is the product of the red term and the green term. Right? What we are doing, we are simply multiplying here. We are multiplying the red term and the green term to get the entire pattern, right? This is precisely the principle of pattern multiplication. If you want to have the radiation pattern due to an antenna array, one of the simplest way of finding it is by multiplying the array pattern, which is given in green, with the pattern of an individual antenna, which is given in red. Is it okay? Had this been loops instead of dipole antenna, had this been small loops, we would have just, what did we need to do? We need to change this red term from the dipole to the loop. Okay, and then we had only 5. Then we had only 5. Because for loops, what you have seen that E theta is 0, but E phi is not 0. For any other antenna, if you have got dipoles for any other antenna, whatever antenna you are using, we simply just change the red term. Any questions? This is called the principle of pattern multiplication. Okay? Exactly. Rather not group pattern, I would say array pattern. Okay? Other than that, you are absolutely right. All of you agree? Achha, one thing for your, one thing I would like to say here in this derivation, it is given in Balanis. This would have been better if we had used theta, okay, because we are doing the entire analysis on the theta plane, right? But since you have done everything with phi, so I did it using phi here. We used phi here, but this should have been better done in theta plane because we are doing it on the theta plane, right? So be careful, little bit careful. Do you understand what I said? Here, if we had written theta instead of phi, it would have been more correct because we are doing it on the theta plane. However, for our previous discussions were on phi, so to make it understand better, I used phi. But the more correct would be have been theta. Okay. Right. So we go to the next antenna. The next antenna is helical antenna. Anybody seen helical antenna? What? Our lab, there are quite a few helical antennas. Anybody has seen a helical antenna? How does a helical antenna look like? Helical antenna is an example of a traveling wave antenna. Why, we will see. Okay. How does a helical antenna look? Have you seen a helix? Okay, helical antenna. Okay, no. Have you seen a helix? How does a helix look like? Anyone? So, an helical antenna looks something like this. You can just open Balanis if you have it with you and see the better picture, because my drawing, especially here, will not be that good. And of course, please go through the helical antenna lectures by Professor Girish Kumar. They are wonderful. Please take out some time and go through his lectures. They're available for free on YouTube and they are absolutely wonderful. There are 3 or 4 lectures, but they are absolutely worth it. So it looks like this. Okay. The diameter of this wire, this is 2a. Okay. The diameter of one of the each loops is d. Okay. The length the length of each turn, rather, the length of each turn which is given is like this. Okay, and finally s is the spacing between each turn. This is s is the spacing between each turn. 2a is the diameter of the wire. Obviously a is the radius. Okay, d is the diameter of the helix, and L0 is the length of one turn. Any questions so far regarding this terminology? Because we will use this S, L, and D throughout the discussion. Any questions regarding this? S, L, and D will be used in the rest of the helical analysis. So please be sure about what they mean. Okay, structure below the antenna is a ground plane. Thank you, I missed it. Structure below the antenna is the ground plane. And below that is the feed. Okay, feed we are not going to use this. Any other questions? So please be familiar. Please familiarize with the structure. If you want, if you have the book with you, you can go through the book. It is given in page 567. Page 567 of Palatis. So you can open this page and just see the structure. And please familiarize with it. Anything else? Okay. It is 5:45, so I will not continue this in the next this session. It's better we'll continue this in the next session. So let me take your attendance, okay, and we will continue in the next. Thank you.